Thanks very much for the introduction from Dr. Dean, and welcome to my talk today. So today, my talk is about Gaussian processes and Bayesian optimization. So I will talk about 4 topics. The first one is just a foundation of Gaussian process regression, including the background and related statistical methods and formulation. Okay. The second part will be design of experiments for Gaussian process models. The third part is a specific topic in computer experiment with the use of non-stationary Gaussian process models in which you may not find those models commonly used in other areas beyond computer experiment. The fourth part will be Bayesian optimization, which is also a specific topic mostly used in machine learning and also sometimes in computer experiments. Okay. So to give a background introduction about the talk today, let me start with supervised learning. Basically, we can think of 2 different types of supervised learning, namely classification and regression. Okay, so in classification problem, you can see on the left figure, I have input points denoted by the location, and the output is denoted by the shape of this 2 different shapes, the diamond shape and the rectangular shape, also in different colors. And the goal of a classification is to find a boundary of this, which can split these 2 subregions. Okay, that means most likely those diamonds fall in one region and the rectangular shapes fall in the other region. Okay, that's for classification. And for regression, we also have input and output, but here output is real valued. Okay, so the input is the x-axis and output is the y-axis. And the goal of regression is to find a usually smooth curve, so that I can use this curve to represent the points with a good fitting. Okay, so that's a regression problem. You can see that in both problems, there is one primary challenge. The challenge is how can we represent those unknown functions with probably complex shape. Okay, so that's one challenge in all supervised learning problems. Okay. The question is how to represent a general function. Well, there are different approaches. Actually, each machine supervised learning method provide a specific way to represent a function. For example, if you consider neural network or deep learning itself is to represent a function. But today, what we are going to talk about is to use Gaussian process to represent a general function. Of course, it has to be a continuous function. Before going to Gaussian process, let me talk about a motivational example. It's a global optimization. And this example is also related to our last topic in today's tutorial, which is a Bayesian optimization. So think about, suppose the goal is to find the global maximum point for a complex function with only limited evaluations available. Okay, so let's consider the figure here. Suppose this is a one-dimensional function and we only observe 5 points of it. And our goal is to find x0 so that this function f, so suppose those 5 points are from an underlying function. Let's say with no error in this case, okay? And the problem is to find x which maximizes this function. There are many applications of this problem with such a formulation. For example, engineering design, we want to find the best product design or process design. And also parameter calibration for computer models such as finite element models. That's what I will discuss later in this tutorial. And also in machine learning, probably one primary application is to optimal tuning for deep neural network, like to identify a proper architecture for the neural network. Okay. So the challenge of this problem is that we don't have any information for the untried point. Right? So on the right-hand side, I also give you a figure that indicate multiple different possibilities of the function, which goes through all 5 points. So that means under those 5 points, the function value is fixed. However, for any other point beside those 5 points, we don't know the function value. So there are so many different choices that gives our basic challenge about how can we identify this maximum point. And in an extreme case, this maximum point can be anywhere, right? So just by introduce a spike like this, because you can introduce such a spike at any single point, except those 5 points. So the maximum can be actually anywhere. So that poses a fundamental challenge of the global optimization. So how much information can we obtain by the observed points, right? So, or how much information can we transfer from the observed point to unobserved point? That's a big challenge. And this challenge cannot be resolved if we do not pose any additional assumptions on this function beyond the continuity. So as I show you, all those functions are continuous, but you can still cannot have any information about where the maximum is. Okay, so basically that means the function space. So in a mathematical language, we say that the function space is too large, so that we cannot solve this problem. And there are different ways to restrict the function space. For example, if you assume this function is convex, then this problem, the difficulty actually decreases by a lot, right? So we have a whole branch of area called convex optimization that can help you to solve any of the problems of that kind efficiently. However, in some problems, we know that the functions themselves can never be convex. Just like this example, if you have a point here, this point makes the entire function non-convex. It cannot be convex in any sense, right? So in this problem, we really need a different constraint or restriction of the function space, but that should also make the problem feasible. And the Gaussian process is one of this kind. Okay. Before introducing Gaussian process, let me talk about a paradigm of statistics. So why I'm talking about statistics, although some of you are more interested in machine learning, I think. So let me just talk about supervised learning. Okay. So for supervised learning methods, there still you can roughly divide the methods into 2 classes. Some of the methods are more statistical, some are less statistical. For example, neural network methods should be considered less statistical. Sorry. Okay, the Gaussian process is definitely a statistical method. That means it is purely constructed based on a statistical philosophy. Okay, so the original idea of statistical modeling is from what we call statistical model. So when I prepare for the slides, I plan to minimize my mathematical symbols and equations. So I'm trying to use graphical tools to represent those math ideas. Hopefully that can ease your ease the logic flow. So here I use this circle to represent what we call statistical model. So each point in this domain is called a model parameter. Basically, we can say that a statistical model is a collection of model parameters. Okay, so that means given a model parameter, it becomes a fixed model. Okay, but in statistics, we don't know which parameter it is. And given each model parameter, we can have a fixed data generation process. Once we run this data generation process, we can obtain our data. Okay, I use this diamond to denote the data. So now we have two directions. We have parameter and we have data. So if consider the forward direction from parameter to data, that's what we call the data generating process, or sometimes we just call it stochastic simulation. This is definitely not statistics, because once you know the model, for example, given a normal distribution with mean 0 and variance 1, then how to sample the data from this distribution is of this kind. So it is not statistics. And what statistics is interested in is the inverse problem, or the reverse direction from data to parameter. So suppose we observe the data. I use a different color because this one may not be anything you can generate in one time given a fixed parameter. So I observe something like this one, and I'm going to decide which parameter should be the best fit from this specific statistical model. So this problem is statistics. How to solve this problem is not as easy or as straightforward as the stochastic simulation, in which you just generate random numbers to according to that distribution, you can do the job. Statistics is not. And there are two general ideas of statistics. One is called frequentist statistics. One is called Bayesian statistics. And what I'm going to talk today is Bayesian statistics. Okay, so the Bayesian inference is an application of the so-called Bayesian theorem, or the Bayes theorem, or the Bayes rule. Basically, it incorporates information from two parts. One is prior, one is data. So the formula is like this one. So what Bayesian theorem can tell you is so-called posterior distribution. Okay, and the Bayesian theorem states that the posterior distribution denoted by theta given data. That means I already observed the data, and I want to tell which parameter should be the correct one. Okay, because I don't have a 100% confidence about which parameter is exactly the true one, because I don't have enough information. So given limited information, what I can tell is the parameter has a distribution in it. The distribution is proportional to the product of the first part is a forward problem, right? Given theta, what the data is, that's from our forward problem. And we said that the forward problem is easier to solve. Okay, so you have this distribution, multiply your prior. Okay, the prior is something you assume. That's our belief about the reality or the parameter space. Okay, so from a Bayesian inference point of view, you can see that the inverse problem is not that hard, right? Sometimes it's as difficult as just as the forward problem. That means if you can solve the forward problem, you can almost solve the inverse problem, not with much difficulty. Of course, there could be some difficulty in terms of numerical computation, but beside numerical kind of part, we don't have like any difficulties in principle or from a theoretical point of view. Okay, so that's a general paradigm of Bayesian inference. So it says that the inverse problem can be converted into a forward problem. And if we go to Bayesian problems, there are two types of settings. One is called parametric Bayes. Okay, so the term parametric or non-parametric is The difference is on how many parameters you have. Okay. So this is not restricted to Bayes, but also to frequentist statistics. We use the same terms. So parametric means that the number of unknown parameters is finite. Okay, if we have, no matter how many we have, parameters we have, as long as it's a finite number, we call the problem parametric. Okay, and for parametric Bayes, the prior. So what is the prior? The prior is a distribution in the finite dimensional space, because I said prior is a distribution of theta. If theta is a finite, or it's a vector or a number. If it's one dimensional, it's a number. If it's a multi-dimensional, it's a vector. Then the probability density function of this number or vector should be either a random variable or a random vector. So that's a distribution in a finite dimensional space. And we have a different type of Bayes setting in which the unknown cannot be parametrized by finite parameters. For example, if the unknown is a function, okay, then a function cannot be parametrized by only finite number of it. So a function is in an infinite dimension space. Okay, so the prior should be more complicated than just a random variable or random vector. In this case, the prior has to be a stochastic process. So what is a stochastic process? Okay, so we consider a simple case. What is a random variable? I just use a very simple case. If you roll a die to get a number, and we know that the outcome or the observation you get from that die is a random number or random variable, right? So that's a basic idea. And if we change this random number to a random function, we can get a stochastic process. Okay, so there is a subtle difference between random function and a random number, because we can view it from different perspectives. The first thing is a random function is a function. Okay, that means if you realize this function once, you can get a deterministic function, just like when you roll a die. Once you release this die, and when it stops, it gives you a fixed number. For example, this one, it gives you 4, right? 4 is here. So once you see the outcome is non-random or is deterministic. So this is also true for stochastic process. So each realization is deterministic. We also call it's a sample path of Z. So it's a deterministic function. However, you can view it from a different angle.
Longer term, possibly, yeah. I don't know if anybody else has thoughts.
Sorry, any questions?
Go ahead, Rui.
Okay, so from a different perspective, we can the function has an input, right? Usually this is an input in a finite dimensional space. Given this x, if we do not suppress the randomness, then this z of x becomes a random variable, just like the outcome of a dice rolling. Okay, so it becomes random. So there are two different ways to view a stochastic process. And what we are interested in here is a specific kind of stochastic process called Gaussian process. So Gaussian processes are ideal priors for continuous functions. Okay, and to define a Gaussian process, we only need two functions. One is the mean, one is the covariance. So mean is a function of just the same x as the output space, and the input space. The covariance function has to be a function of two arguments. Each one is a variable in that same input space. Okay, and the notation for Gaussian process is just GP. So we put M and C. Okay, and why we said those priors are ideal for continuous functions because we have a important theorem saying that if M and C are continuous, then this Gaussian process has continuous sample path. So that's why we use those stochastic process for priors for continuous functions. And this one is just a term. We call this GP centered if the mean is 0. So mean is 0 is a simplified version of a GP with mean 0 with centered. Okay. And in Gaussian process modeling, perhaps one of the most important class of Gaussian process should be the stationary GP. So basically, the stationary GP is adding a further restriction on the covariance part of the GP, as well as the mean part. The mean part can be modified. We will talk about it later. So suppose the mean is 0, is centered, and the covariance can be represented because this C you can see is a bivariate function. But actually, this bivariate function can be represented by a univariate function k. So this k depends only on the difference between x1 and x2. Okay, if this is true, then we call the GP stationary. So what does it mean? It means that if you add some, for example, if you plus 1 on x1 and x2, this 1 will cancel each other once you take the difference between two of them. That means the probability structure is invariant in translation of the space. So that's the idea of stationary. Now the question is why we are using stationary processes for the priors commonly. So the reason is that in Bayesian statistics, we are trying to use weaker priors. Sometimes we call it non-informative priors in some problems. If you have a background in like basic statistics, that's what we are normally using. A non-informative prior, the meaning is that we want to introduce less like subjective information into the statistical inference problem, because if we are not sure about what kind of prior it should be, then why not just use a non-informative one? So stationary GP somehow serves as a non-informative prior because we do not know in which part the function is like it has a bigger magnitude, in which part it is smaller. If we don't know that, we just use a stationary one. That means we put an equal weight or equal importance at each place of the space. So that's the idea of using stationary GPs. And once we determine the GP, what does there is one question from the audience. What does K mean here? This K is basically K is a univariate function. Let me talk it in this way. So for stationary GPs, on the previous slide, I used K, but now I split this part into the product of two parts. Basically, what I do is I factor out sigma square so that the latter part has 1, the value is 1 at the origin, because the origin must be part of it. Okay, so then I can give specific meaning for each component. Sigma square is called the variance of that process, and phi is called the correlation function. So the correlation and the origin is 1. That means if you compare one thing with itself, they are always equal. So the correlation is 1. If you compare ample and the pair, the correlation is lower, right? So they still have some correlation, but they look differently. So the correlation is less than 1. There are some commonly used correlation functions, the Gaussian correlation and the Matern correlation. You can see that in each family, we have additional parameters that are undetermined. So this theta is a scale parameter. Basically, this scale parameter means that we are stretching the input space, right? X is multiplied by theta. That means you are either pull the space or push the space. That's for Gaussian. So an important property, an important sample path property for Gaussian is that they are infinitely differentiable. So that's a sample path property for Gaussian. And if you don't want the sample path to be that smooth, perhaps your underlying function is do not have infinite many of derivatives. You only have finite derivatives. You can consider this Martin correlation family, in which you can control the smoothness by specifying this nu. This nu actually is can be any positive number. It's called a smoothness parameter. Here we encounter a special function. It's called modified Bayesian function. Those functions can be implemented. I already implemented in R and MATLAB, so you can just call them directly. And another thing is that you can see that those correlation functions are always positive. We don't have negative correlation. And that's also kind of assumption that in spatial statistics, we believe any 2 points should have positive correlation. Okay, so on this slide, I show you a few examples about the sample path with Martin and between Martin and Gaussian. For Martin, I give you different new value from 0.5, 1.5, and 2.5. You can see for 0.5, this function is non-smooth. You can see many spikes on it, right? Actually, when I plot those GP sample paths, I can only give up to some precision level, right? That means I need to discretize this input space into a few nodes. This could be 100 of them, but for the very rough functions, it's still not enough. If you further refine your grids, you will see more spikes. Okay. And also you can see as this nu increases, you get more smoother curves. If nu is 1.5, it's smoother, and 2.5, you can see almost the same as the Gaussian case. The Gaussian case is equivalent to Martin with infinite smoothness. Okay, but you can see there is a small bump somewhere on the curves that indicating the function is not as smooth as the Gaussian part. Okay. So that means with the Gaussian process prior, basically you can get different functions with totally different sample path behavior. So Gaussian process should be a broad type of priors for continuous functions. After talking about one-dimensional case, we should go to a multi-dimensional case. How can we construct multi-dimensional correlation functions? The idea is to use one-dimensional functions to build those multi-dimensional correlations. There are two major strategies. One is called isotropic correlation. Basically, if you choose a Gaussian or Martin correlation, and use this like this double vector line to denote the Euclidean norm, then define it in this way. So this phi of x should be a multi-dimensional correlation function. This is called isotropic correlation. The second one is product correlation. Just by taking the multiplication of each entry. So this x has entry 1, entry 2, all the way to entry d. Okay, and send each entry into a one-dimensional correlation and then take the multiplication of all of them. And then you can get another correlation. This is called multi-product correlation. These two ways are feasible methods to build multi-dimensional correlations. Of course, there is one thing that these two methods give you the same result. That is the Gaussian case. Okay, because the Gaussian is x to the e to the x to the power of 2. Then these two actually will give you the same result if the kernel is Gaussian. And I show you some comparison about the sample paths of the given by isotropic kernel and product kernel. Of course, we only consider Matern because for the Gaussian, they are the same. So there's nothing to compare with. Okay, so you can see that this is a non-smooth case with nu is 2.5, and this one is a smoother case with nu to be 2.5. Almost you cannot see a clear difference between these two cases. And this is because it's two-dimensional. It's just two-dimensional. So in low-dimensional case, you cannot see a major difference between two different constructions, but higher dimension, these two are quite different actually. However, we cannot visualize that difference. So next, let me see any questions you have. On slide 11, what's the difference between the first row and the second row? I just implement the same thing twice. So because each one is a random function. Each one is a random function. When I generate it twice, I get a different different function. So there are two independent sample paths from something in common here. That something is the smoothness, right? Both of them are very rough. These two have the same smoothness. Although the shape are totally different, they enjoy some common smoothness properties. Okay, so for non-centered GP, actually the idea is simple. Just consider centered GP sample path plus your mean value, you get new sample path for non-centered GP. So that's a simple addition process. Okay, so now let me talk about machine learning with GP models. Here is a figure I took from a paper by Simon Mack et al. So it's about a GP surrogate model for so-called large eddy simulation. That's computational fluid dynamics. Okay. So you can see that this figure basically shows that the upper part is emulated. The upper part is called emulated. The lower part is called simulated. Simulated is the truth. Is a truth, and emulated is using Gaussian process to predict. So you can see that the prediction is quite good. So you can see the difference is minor, and it captures the main flow of this large eddy simulation. So first we'll talk about model. Gaussian process regression, also known as kriging. The model is yi is equal to f of xi plus ei. Okay, so f has a prior. F is an unknown function, right? So the goal is to reconstruct f. And because f is unknown, in view of Bayesian statistics, we put a prior on it. The prior is a GP. And here, we use mean zero. Mean is zero in this case. And that's why we call it simple kriging. Okay, so we have different types of kriging with just different parameterization of the mean part. And the EI is an IID with mean zero and the finite value. This tau square is a finite number. Okay. And there is a specific case in which the tau square is zero. That means we don't have this EI. So if this EI does not present in this model, the reconstructed curve f hat should interpolate f and the points we observe because there is no error in each point. Okay. And the theory for kriging relies on this distribution called multivariate normal distribution, which is a multivariate counterpart of the univariate distribution, the normal distribution with mean mu and the variance sigma square. I think you are familiar with the univariate case, but for the multivariate case, I just give you some basic idea. It also has only two parameters, but one is a vector, one is a matrix. So the vector is a mean, still called mu, but now it's a vector. And the covariance should be a matrix. Okay, I use sigma, this capital sigma, to denote the variance. And there are some very good properties of multivariate normal distributions, and I'm not going to go through all of them. What I'm going to show you is that the PDF and conditional distributions are available. You do not need to remember those formulas, and not needed in this tutorial. The only thing you need to know is that we have explicit formula for all of them, and that's it. Okay, and the important thing is the conditional distribution. So what is a conditional distribution? So think about this one is a vector, and suppose we partially observe this vector. We observe part of it, and we want to make an inference with the unobserved part. We should give another distribution, and a good property is that that distribution is also multivariate normal with a new mean and a new variance. Each one has a explicit formula. Okay, and this is the idea how we can solve the simple kriging problem without error. So if sigma, if the variance tau square is 0, then what we can do is calculate the conditional mean and conditional variance using the formula on the previous slide. So we can get something like this one. Okay. So for the conditional mean part, it gives us a curve. This curve will interpolate the data. So that's what we call interpolation property. And the conditional variance will give us a band which can quantify the uncertainty of our prediction. So it looks like this one. That's what a figure I took from the internet. Okay, suppose we observe some points, each one denoted by a square. Then we can use the first formula to reconstruct the mean function denoted by the red curve. And for each point, we have a confidence bar given by the variance because each point is also a normal distribution. So we can have a confidence bar at each point. Okay. And this red curve serves as a natural predictor for the underlying function. Okay. So that's a general idea of kriging. And here, maybe you can see that this formulation or rho is it can be represented in an analytical or in an explicit way. There is some computational challenges. So, for example, if I consider predictive mean, actually for the predictive variance, we have exactly the same issue. Okay, so this mean can be split into two parts. The first part, I solve this equation to get this u. Okay, I call it a training step because in this step, I do not need to give an extra untried point. Okay, the next point is, the next step is the prediction step. I need to give a new x, which is unobserved. And that point is, the y value is unobserved. And I just compute this function. Okay, this function depends only on this x and this u. Of course, this phi is a known function. Okay, so that's the basic flow for solving the kriging problem. However, if it turns out the computational complexity, the time complexity actually is quite big, even if the formula is very simple. So here you need to invert this matrix or solve this linear equation if you are using Gaussian elimination. That's the direct method. You need n to the n cube training time. Okay, that's unacceptable. And for prediction, even if we already obtain this u to predict for a new point, we still need big of n time for prediction. So prediction, n is the sample size. Okay, so because we need to end up all those terms. So both of them are unacceptable for huge n, right? So if we just consider the prediction step, if you use a neural network or deep learning method to do prediction, of course, the prediction is independent of how many data points you have from the training step, right? So that's a big difference. And that's why we cannot consider this GP method if you have a really big N. Of course, there are some work, actually many existing works are discussing how to improve the computational speed of kriging. But this is still a challenge, especially when some other alternative methods are available. And another thing is that K can be nearly singular when N is large. That means if this matrix is nearly singular, solving this equation can be difficult in terms of numerical error. So even if you can use this time to find the solution to this equation, this solution can be inaccurate. The round-off error can easily accumulate it because there could be some singularity issue in it. Okay. And one thing to enhance the numerical stability, which can address the singularity issue, is to introduce the so-called Nugget effect. So instead of inverting this K, we consider K plus something on the diagonal entries so that the stability can be improved. Okay. A cost of doing this is that the predictor now is no longer an interpolant. And this approach is equivalent to the predictor given the noisy data, with the noise variance to be lambda. Okay, that's a Nugget effect. And the next one is universal kriging. The only difference is that we replace the mean part from 0 by this one, a summation of it's a linear combination of basis functions. So this part is just like a linear regression. Okay, so what we want to learn are the regression coefficients beta. And parameters can be estimated by MLE or Bayesian methods. Okay, and prediction can be done by plugging in the estimated parameters or using a full Bayesian approach. So let me briefly talk about how to do the MLE, and this is MLE, and next slide I will show you how to do Bayesian. So for universal kriging, we have 3 types of parameters: beta, sigma square, and theta. Okay, so the goal of parameter estimation is to estimate 3 of them simultaneously. And this is done by maximizing the likelihood function. So P of the observed Y given those 3. So this part is actually the PDF of the multivariate normal distribution, because this Y follows the multivariate normal distribution. So you don't need to recall what the function is, but just let you know this part is available. Okay. And of course, maximization is not easy. Usually this is done by gradient descent or gradient ascent algorithm, because we want to search the maximum for it. Okay. This is MLE. This one is multivariate normal. Okay. For Bayesian, of course, the first step, we need a prior for those distributions. Okay. The next step, what we do is use the Bayes rule to determine the posterior distribution, which is proportional to this multivariate normal times this your prior. And the Bayesian computation should be done in with some specific algorithms, such as Markov chain Monte Carlo or variational inference. Markov chain Monte Carlo is should be the benchmark of the Bayesian computation methods, which is should be considered as the most accurate method. And variational inference is an emerging method that is popularized recently, which is excellent in handling big data. If you have a bigger data, probably Markov chain Monte Carlo is not computationally efficient, but variational inference can handle this problem. Okay. There are some philosophical discussion about why to fit a deterministic function with a GP, right? So think about if the f is deterministic, perhaps it's from a computer simulation. Why we still use a GP, which is random to fit it? So there are different ways to justify it. You can consider the Bayesian way, as I said, GP is just a prior, or you can consider a frequentist perspective to show that GP is just a methodology which works for many different problems, right? So each time you use it may be regarded as a test of that method. So if you implement 100 times, there should be 95 times of them to get you correct answer or something, right? You can also justify it from an approximation theory point of view, which is more theoretical. I'm not going to discuss this part, but one thing I'm telling you is that from approximation theory, there is also good results for GP. It's unlike neural network, probably you can not tell much about the accuracy or the kind of the coverage of things. But for GP, there is indeed very good theory about it. Okay, so we talk about regression problem. Now we consider other types of supervised learning problems. In a general supervised learning problem, what we do is to consider a loss function. It depends on what kind of problem you are looking at. Right? This is just general supervised learning, so nothing special here. Just consider a loss function. And loss function is defined by some L. We have two arguments. Y is your observation, and X is your input. Here I use f of X here. So this one defines the loss function given the learner f. Okay. Now under Gaussian process prior, we consider f to be following a GP, just as a universal kriging did. Okay. So in this problem, we can generalize the regression to an arbitrary supervised learning problem with GP. And how to solve this problem? Basically, the idea is so-called data augmentation. Data augmentation is a term in Bayesian computation. So the idea is that we augment some intermediate variables. Here is f of xi. Here, f of xi. We denote f of xi as zi. Then this problem can be decomposed into two parts. The first part is the empirical loss, which is the same as a general machine learning problem. The second part is the GP regression, right? Because zi is f of xi, then if zi is known, then this problem go back to the Gaussian process regression, as we discussed earlier. Okay. So the training methods, we can consider frequentist way or Bayesian way. Of course, they are related. So in a frequentist way, we can consider a panelized or regularized loss function. So the first part is the loss function. We have z here. So z, because we augmented, this is called data augmentation. That means originally z is not a parameter, but now we regard z as parameters. So once we take the minimization, we need to also minimize with respect to z. And this part is the loss. And the next part, which is a penalty, is the negative log likelihood. Because if we don't have loss here, just like the interpolation problem, what we are doing is to maximize likelihood, right? So here, when we talk about minimization, it's to minimize the negative log likelihood. And there is a one-to-one correspondence between this problem with another method called kernel learning problem, kernel learning method. So given by this format. So here is the norm in the so-called reproducing kernel Hilbert space, just for your information. If you know this kind of method, you can establish a relationship between two of them. So what I'm saying is numerically or computationally they are equal. It doesn't mean the philosophically they are equal. They are not equal, because one is from a GP, one is from a kernel. So only the computational results are the same. Okay. If you prefer to use the Bayesian approach, this can be done in a similar way, just by recursively implement the Bayesian rule. Okay, so what we do here is, first this posterior is proportional to y given those parameters, right? So y given those parameters, actually you can omit those parameters because z, once you given z, it's like a Markov process. Given z, those parameters are independent of this y. And multiply other two terms. So here should be the probability of z beta sigma squared theta, and then I do it again. So I split into these two components. So that's a general application of Bayesian rule, so you can solve the problems of this kind easily. Okay, the rest of it just to do Bayesian computation. Of course, you need to choose a method to compute the posterior density or to sample from the posterior density. Okay, so before our first break, I'm showing you an example, which is the classification. Because at the beginning, I talked about both classification and regression, right? So this one is classification. I consider logistic regression. So it's what I call GP-based logistic regression. So in this problem, y takes only two levels. In logistic regression, it's easier to label these two levels as 0 and 1. But they don't have specific meanings why you do 0 or 1, just for the sake of convenience. And the input x is real valued. And the likelihood given z is the augmented variable. This is a standard likelihood function for logistic regression. Of course, you can simplify it, but that's the original form. Basically, this one is the probability. And this one, you can see is 1 minus the first one, right? The summation of these two is 1. That means the total probability is 1. So this one is the probability of y taking the value 1. And this one is the probability of y taking the value 0. So you just multiply all of them, you get the likelihood function. And if we are using Bayesian method to solve this one, of course you can do the frequentist way, just take the log likelihood as the penalty, negative log likelihood as a loss function, and also you have the likelihood for the GP part. Okay, that's easy. And if you are using the Bayesian method, basically you can also write down the posterior given by multiplication of 3 terms using the Bayesian rule. You can do that. Okay, so then you can do MCMC to sample from the posterior distribution. That's for parameter estimation. And for prediction at a new point, what we do is to sample z new from the new posterior distribution. So F is the posterior, is the sampling from the posterior distribution. So we can sample this one because F is is this one. F is a GP, right? F is a GP. Now the next thing is to sample Y from the binary or the Bernoulli distribution with this probability mass function. Okay. So that's the prediction, the learning and prediction for GP-based logistic regression. Let's have a short break, about 5 minutes. If you have any questions, please feel free to ask. Thank you. Let's continue. So now we move to the why use a Bernoulli? So one of the audience asked this question because in logistic regression problem, it's a classification of 2 classes. Right? We only have 0 or 1. So if a distribution only takes 2 levels, that must be a Bernoulli. Okay, so okay, thank you. Okay, so next is a summary of what we have talked about so far. When to use GP models. Okay, so GP models are suitable under a few conditions. Well, I think GP is not very commonly used. It is commonly used, but not as frequently used as some other machine learning models, such as neural network recently, right? So because there are some constraints, you need to fill in that class so that GP models are good. At least a few of them. Okay, the first one, underlying function has to be smooth, of course. That must be true. For GP-based logistics, let me finish this slide and then go back to your question. Thank you. So 5 conditions. The first one is underlying function is smooth. The second one, data size has to be moderate. We cannot handle too many data points. Okay. The third one, the input dimension is not too high. Also, there is some intrinsic reason, also from both theoretical and computational. So input dimension should not be too high. And fourth one, the signal to noise ratio should be high. If signal to noise ratio is really low, you do not need to use GP model. Maybe the linear model is the best way to fit the data. And the fifth, uncertainty quantification is of interest. If you are not interested in UQ, then probably you do not need to consider a GP, which is more complicated. Okay, so if all of those 5 conditions are fulfilled, I believe that you can hardly think of an alternative method of GP that which can beat GP. So that's the most ideal cases of the usefulness of GP.
Ray, there are 2 questions.
Yes.
In the chat.
Yeah. So yeah, I saw the questions. The questions are, yeah, how large is moderate data size is to use GP in practice? Well, it depends on the method you are using for training and learning your data. So if you are using Gaussian elimination, of course, the data size cannot be, I think, less than 10,000. You cannot handle more than 10,000 data. But if you are using an improved algorithm, I don't know which one you prefer, but there are many of them. Those are approximate. So basically, the idea is to solve the linear equation, right? If you can solve that linear equation efficiently, of course, the data size can be larger. So it really depends on what kind of specific algorithm you are using to solve that problem. But cannot be as big as what I heard from some speakers in some other conferences. They claim they can handle like 1 million. So that is really big. But it depends on the accuracy level you want to achieve and which algorithm you prefer. The signal to noise ratio. The idea is that signal to noise ratio means that if the noise is small, then GP is good. The extreme case is the interpolation, right? So in interpolation problem, I don't think any other method can beat GP. Or very few of them can beat GP. So if there is no noise at all, okay. Some typical areas, spatial statistics, so in which GP is natural tool to capture the spatial temporal correlation. And in Bayesian optimization, what we are going to talk about, and surrogate modeling for complex computer models, we are also going to talk about those two things. And back to the logistic regression. What's the question? Let me read. Logistic regression based on, for the GP-based logistic regression with a fixed X new, we have a random output Y new. Yes, this is a random. Well, Well, this is the same because I'm using Bayesian method. If you are using a Bayesian version of logistic regression, you are also going to draw a random output. So this part actually is the same. If you don't want a random output, you can just stop from the first step because the first step will give you a probability. This F is corresponding to a probability, or you can consider the part inside the parentheses. Inside the parentheses, it gives you a probability. Okay. So I think the general training and the prediction for the logistic regression should be similar to the usual one. The only difference is the Gaussian process prior is implemented. Okay. If no more questions, let me move to the second part, the design of experiment. So the basic idea of design experiment is to find the input points, input sets, which can maximize my prediction performance. This is based on an observation that the performance of GP can be affected or highly relying on the input points. So here I show you two figures. I'm using the same number of points to fit the same function, okay? And the blank curve is the underlying truth, and the blue curve is the reconstructive function. You can see that I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I have 10 points on each figure. But you can see that the prediction performance are different. This difference is caused by I choose different input points. On the left-hand side, the input points are equally spaced. And on the right-hand side, they are randomly chosen. So you can see that causes a huge difference in the prediction performance. Okay, so the DOE actually, the name is from is rooted in the very early work by R.A. Fisher, who proposed 3 fundamental principles of experimentation, and I think replication, blocking, randomization. But these principles are not applicable for GP models simply because we are dealing with different models. Okay, so what we are doing here is based on a different considerations. Okay, there are in general 4 different strategies to build designs. The first one is geometric, but just by using geometric principles or considerations. The second one, projection. The third one, tensor-based designs. The fourth one, optimal designs. So distance-based or geometric-based criteria. So I show you 2 of them. Actually, each subclass has many methods. I can only show you a few of them. Okay, here I show you the so-called minimax distance design and maxi-min distance design. So each one is based by maximizing or minimizing a certain distance. One is called field distance. Basically, it means that whether the points can fulfill in the region we call the experimental region. Basically, it's think about an untried point, the distance between an untried point to another point. Okay. So you can think about the bus stations in like a city, like in college stations. So suppose those are the bus stations, and imagine one person can start with any point in college station and how long he has to walk to the closest bus station. So this distance is a so-called field distance. And the separation distance is simply just the distance between 2 closest points. It's just like our social distancing, right? So two people are very close to each other, then this distance is low. So we want to minimize the field distance and maximize the separation distance. Of course, these 2 goals cannot be achieved simultaneously, but somehow they are not too much conflict with each other. So you can maintain the field distance to be relatively small and the separation distance to be relatively large at the same time. This is purely based on the distance, okay? And this one is a simple design. It's called full grid design. Sometimes we just call grid design. Basically, we just staking the design into like rows and columns. So they are aligned with each other, just like a matrix. This is a two-dimensional case. And in higher dimensional case, they are hypercubes. So if we justify these designs in terms of the geometric, just in terms of the field and separation distance, they are not optimal, but they are up to a constant close to the optimal. So not too bad from a geometric point of view. And another reason I want to show you this one is those designs actually reason naturally in certain problems like imaging. So each point represents one pixel. Like remote sensing, of course, also imaging data. So each point is just one location. So I have a matrix of this kind. So in those problems, I cannot choose design, but what I obtained is naturally a grid design. Those designs are good for isotropic kernels because isotropic kernels, the accuracy only depend on the geometric things I have shown on the previous slide, the two distances. However, for product designs, it's a different story. For product kernels, I mean product. When I say product, I mean product matter, because product Gaussian is the same as isotropic Gaussian, so there's no difference. For product matter, those designs are less accurate. One major reason is that those designs do not have good projection properties. Projection means once you consider the projection onto a one-dimensional space, you can see these 3 points overlap with each other. If I consider only the x-axis, right? So if I project onto 1D, I only have 3 points. So that means I lose a lot of information in it. That is a downside of grid design, but also we have an advantage of grid design, not in terms of prediction accuracy, but in terms of the computational efficiency. Okay, so the computational average. Now I'm going to introduce the different performance measure. We talk about prediction accuracy. We want the most accurate one. But as I said, the GP itself somehow suffers from the computational issue. So the computational efficiency is also important, right? And the good thing for those design, for the grid design under the product kernel is that the computationally we can leverage one spatial operation of matrices called the tensor product, also known as the Kronecker product of matrices to accelerate the computational efficiency by a lot. So the tensor product, I'm not going to show you the mathematical definition because that will introduce a lot of notation. But the simple thing is just look at the dimension. A 3x3 matrix tensor another 3x3 matrix will give you a matrix like this one. So it will be a 9x9. So each small matrix of it basically is one element from the first matrix multiply the entire second matrix. So each one is 3x3, and you are staking them together, you get a 9x9 matrix. Okay, and the good thing for the computational part is in terms of linear algebra, you can prove that when you are operating using the tensor matrix, basically you can somehow transfer back to the small component matrices. Okay, so for example, consider kriging prediction with those 9 input points. If you are using direct Gaussian elimination, the time complexity is 9 to the third because you are going to invert a matrix which is 9x9, this matrix. But actually inverting this matrix is equivalent to inverting this small one 3 by 3 and inverting this 3 by 3 one, and then take the tensor product, which is not very costly, not as costly as inverting a matrix. So in this case, the computational complexity reduced from 9 to the third to 3 to the third, so which is a big improvement. And remember that here I consider 3 by 3, right? And actually you cannot just have 9 points. Maybe it's 10 by 10, right? Now you reduce your computational speed from 10 to the 9th, 10 to the 6th to 10 to the 3rd, right? That is from 1 million to 1,000. That's really a big improvement. And not to mention, this is just 2-dimensional space. In high-dimensional space, that's an even bigger improvement. So that's a promising part from the computational point of view for the grid designs. And of course, we said that if you don't consider, if you are not do not care about the computational cost, you only care about the accuracy, of course, this Latin hypercube design should be of your interest. Basically, it's a subset of the full grid design, which has 9 points. What I do is I take a subset of it by within each line, within each row and each column, I just choose 1 point, one single point. Okay. So this design is called Latin hypercube design. Of course, it does not enjoy a computational a good property, but in terms of the projection, it's very good because when you project this design onto each of the one-dimensional space, you still get 3 points. You lose no information. And this one is purely combinatorial. Of course, there are many different choices. So you can prove there are n factorial different choices because you can permute each 2 rows to still get a Latin hypercube. But usually we are incorporating the Latin hypercube criteria together with the the space filling matrix, for example, the minimax criteria. So we can get some specific Latin hypercubes, for example, the minimax Latin hypercube. And the optimal designs are the ones that directly minimize some errors. But to do this one, you need to pre-specify the parameters of the GP model. So once you know the parameters of the GP model, you can calculate this one, and you can then do a numerical search to find the best D, which can minimize the, for example, integrated mean square error or the maximum of the error. But those ones are less commonly used because to find those designs, it's too computationally expensive, and we do not know why they are important if we are still sure about what kind of parameters those GPs should have. Okay. The last class is what we call sparse grid designs. Basically it's an improvement, or it's improvement from the full grid design on the right hand side. I say the full grid design is computationally efficient, but it has a deficiency that the prediction is not good. And sparse grid takes a subset of it. It's a suitably chosen subset of it. It has better projection properties. Although if you project onto one direction, you can see some of the points are overlapping, but you still have this many points left. So the projection properties are better than the full grid designs. And also matrix inversion can be done efficiently by a specific algorithm called Smollett algorithm. So that's a good thing for those designs. Okay, so next part is about some the use of non-stationary covariance in computer experiment. So in computer experiment, basically the goal is to do a so-called surrogate modeling. Suppose the computer model is complex, and we cannot just simply run it over and over until we have a good understanding about the function relationship. If we cannot afford their computational cost, we can do in this way. We choose some input points and we build a surrogate model. Okay. So there are two specific problems I like to mention today. One is multi-fidelity. So this is perhaps one of the unique problems that is encountered in computer experiments. So think about finite element. We can have different mesh size. So on the right-hand side, we have a finer mesh. Left-hand side, we have a coarser mesh. The finer mesh will give us a better prediction, but it takes a longer time to solve the problem. Okay. And the goal of the data science for this kind of problem is to integrate output from different fidelities. Okay. So what the literature suggests us to do is to use this kind of model. So the model links all fidelities. Suppose we have 8 different fidelities, and we can do regression. It's kind of time series autoregression. So the next level is built by the previous level plus some error term. Okay. And each of the unknown error term, sorry, this should be 2, should be a different subscript. We build each of them as a GP, so we'll assume. So this one can give us a model which can fit the data from multi-fidelities. Okay. There are some general guidelines. I think today I don't have enough time to go through this part. And another problem is calibration of the computer model, which is about to identify the model parameters in the computer model. Okay, so when we talk about computer model, usually we are solving like a physical system, but usually this physical system comes together with something unknown, like the permeability, conductivity. Those are the parameters of that space we may not know. And calibration is to adjust, is to actually compare between the computer output and the physical output and find the best fitting of theta value, which can give the best matching of the two data. Okay. And this one is a popular method from the literature. So the model is like yi, the physical part is given by a zeta plus epsilon. Okay, it's just like a regression problem. Zeta is unknown. But in the next step, the model decomposes zeta into 2 components. One is this part is computer output. This part is so-called discrepancy, which states that the computer experiment cannot perfectly mimic the physical process. That's why we need this one. And this equation is true only if the calibration parameter is correctly chosen as a theta 0. Okay. So once you have this model, you can also write down the likelihood function. You can write down the posterior distribution so that you can estimate theta. Okay, so the last part of the talk today is Bayesian optimization, which is a global optimization method widely used in machine learning, especially in recent years. Many people are using this method to do optimal tuning for artificial neural network or find the best architecture of the neural network. The general formulation of this problem is a global optimization. Okay, so as I show you at the beginning of this talk, the goal is to find the maximum value or the maximum point, it doesn't matter. Sometimes I want both the x value and the f of x. Okay, so this optimization is so-called global optimization. It's not local optimization. So what I mean is I need to find, or I need to, the ideal way is to consider all different choice of x so that this f is maximized over the entire space. And Bayesian optimization methodology are commonly promising if you can see that those are pretty similar to what I said for the conditions when it's promising to use GPs, because this Bayesian optimization method itself relies on Gaussian process, so it has a very common kind of promising region. Okay. First one, the input dimension is not too large, typically no more than 20. You cannot consider a really high dimensional global optimization problem. I think the problem itself, it may not be, the formulation itself has some issue. If you consider really high dimensional problem, you can, the search space is just in general too big. So I don't think there is a method can solve that problem in general. The second one, the objective function has to be continuous because we are using GP. And the third one, we don't have any specific structure assumed for f. For example, f has to be definitely non-convex. If it's convex, we don't need to bother using this kind of complex technique to solve this problem. And the last one actually is most important. F has to be expensive to evaluate. Because in this optimization problem, actually Bayesian optimization is not a specific algorithm. It's more like a framework of solving these problems. I will show you later. So this framework requires that F has to be expensive to evaluate, either to be cost you a lot of money to do that or cost you a lot of time to do that. If F is easy to evaluate, for example, just like an analytic function, then we do not use this kind of method to do it. Okay, for example, if the question is how to best train our PhD students, then this is definitely a function which is expensive to evaluate, right? So say you have an idea to train a PhD student, but if you want to validate your idea, it may take you a long time, like 4 to 5 years until the PhD student graduate, right? So it takes you a really long time. So that's an example of an expensive function. Also, if you're training neural network, of course, training a neural network is expensive, right? So it may take you a few hours to a few days to get a training of a specific neural network. If you want to change the architecture of the neural network, you have to train it for another time. So each time takes you a few hours. This F is also expensive to evaluate. Applications, as I said, optimization for complex computer model output. So that's for computer output, and reinforcement learning and architecture configuration in deep learning and so on. Okay. So the general idea of Bayesian optimization is, the first idea is sequential optimization. Sequential optimization is quite similar to our general optimization problem, right? When we say something about optimization, basically we are trying to evaluate this function one point after another until convergence or until we achieve certain promising properties, right? Then we can stop. So sequential optimization is the same, but first we need to have a GP prior. That's the first step. That means for this function f, because we don't know anything of f, we need to choose a prior for it. And in this case, we don't have any information about it. Usually we just use a stationary GP as a prior of f. And the second step, we need to choose an initial design of it. Here I consider a max-min Latin hypercube design. Okay, so the reason we need the initial design is that we need to build an initial GP model for F. If we start from nothing, it's not the most efficient way because initially we don't have any information about it. So we need to get an initial exploration about what the function would look like from a very rough scale. So in the second step, we have those points and then we evaluate F over the initial designs. So now we have 1, 2, 3, 4, 5, 10 points. So that means I need to evaluate, when I need 10 evaluations in the initial stage. And then we can move to our iteration step. Okay, so update the posterior. First, we update the posterior. Once we have the observations, we can get from the prior to the posterior. We can have a posterior of F. And the fourth step is to determine the next point by optimize an so-called acquisition function. There are different acquisition functions depending on which criteria you are using. I will show you 2 of them. And more of them, there are more of them, but I will leave it for you to consider. Okay. So on the figure, I show you this star point, which is a new point. This point is obtained by optimize an acquisition function. Then I have a new point. Then I update this function. I evaluate this F and this specific point. Then I update the posterior of this GP. Okay. Once I update the posterior of the GP, then I can determine the next point. And then I do back and forth between step 3 and step 4 until either the budget is used or a certain accuracy level is met. So I may get this points. Somehow I may find more points around this region because this region is most likely to have an optimal point close by. Okay, so that's general steps for the sequential optimization. And the next topic is the acquisition function. The acquisition function is a function of the input space. Okay, it also depends on the GP prior. And let me first show you the notation. So I use AN to denote the acquisition function given the first n points. So for example, at the first step, after I choose the initial design, I have 10 designs. Then this n, the first n is 10 because the initial design is 10. So I have the acquisition function defined in some way I will show you later. Okay. And the next input point is defined by another global optimization problem. This global optimization problem is to maximize the acquisition function globally to find the x value, which then send this x to be the next input point. So you may ask the question, why do we do this? Because initially we want to solve a global optimization problem. Then we come up with another global optimization problem. What's the benefit of doing that? So the benefit is that this function is easier to evaluate. This is not an expensive function. Or compared to the original F, it's less expensive. So solving this global optimization problem should be easier than solving the initial one. For example, if the initial one is the performance of the deep neural network, right? If you want to get that performance, you need to do all the training for the neural network. It costs you like 3 hours to do that. Then to global optimize that function is much more difficult than globally optimize this acquisition function I will show you, which has an analytical form. Okay, so that's the idea of global the Bayesian optimization. Then how to build a global optimization? So the idea is to balance the exploration and exploitation. A related problem is the so-called multi-arm bandit. So I use this commonly used. This is a commonly used picture to describe the multi-arm bandit problem. So the idea is that I have many arms. Each one I can pull the arm once by choosing one of those bandits. So the question is, which arm should I pull in order to get a higher reward? So at the beginning, you don't have any information about which machine will give you a higher reward, right? So you are going to try each of them. That's a process called exploration. Okay. And later on, you may be able to identify one of them is more likely to be have the higher reward. Then you just stick to that specific arm. That part is called exploitation. So in mathematical language, exploitation means that place the arm with the highest expected reward. Then expected reward means that you have a prior, then you update your prior. You get a posterior, and from that posterior, you can take the expectation. And exploration means that you place the arm with the highest uncertainty. It's also about the posterior, right? Initially, suppose you are using an almost informative prior. Then the arm, which has never been played, has the highest uncertainty. Then I'm going to try that. If I haven't done it yet, right, why not try it once? So that's for the multi-arm bandit problem. For Bayesian optimization, actually it's an even more difficult problem than multi-arm bandit, because in this case, we have infinite many arms, because our input space is a continuous region, right? So like in this figure, we only have 1, 2, 3, 4, 5, 6 arms. So we only choose 1 out of 6. But in Bayesian optimization, we are choosing 1 out of infinitely many possibilities. But still, we can define exploration and exploitation. So think about this problem. So we observe 5 points in this interval, okay? And I fit a GP model, and the red line denotes the mean, and the blue curves denotes the upper confidence band and the lower confidence band. Now, the exploitation means that we want to sample the point with the highest expected value. So expected value is the red line, is a red curve, right? So if you consider exploitation only, you need to choose this point because this point has the highest expected value. And another idea is to consider exploration, in which you want to sample the point with the highest uncertainty. So it definitely should be in this region, because this region has the highest uncertainty. That means although the expected value, the average value is not as high as the left-hand side one, but there is a potential because we don't know, we haven't tried this region yet. And as the model says, this region, the function in this region, the function value is uncertain. So pure exploration is this point. Pure exploitation is this point. And the pure exploration is this point. So, and a good Bayesian optimization criterion should make a trade-off between the pure exploitation and pure exploration. So we are actually doing neither pure exploitation nor pure exploration. We need to combine them together. Okay. And the ideas, actually there are many different ideas to combine them. So I think I will show you 2 of them, but I think definitely you can come up with your own ones if you just think about it for a few seconds. Okay, the first one is so-called GPUCB. Actually, it's very simple. Because, as I said, I want to make a trade-off between exploitation and exploration, right? So that means I need to consider both the red line and the difference between these two blue lines. So why not I just consider the upper blue line, this point only, right? Because this point is the sum of this red line and the difference between the red line and this blue line. So I get this. Why not use this point as the acquisition function? So if you are doing this one, you are going to the so-called GPUCB. Okay. Just consider the alpha upper confidence bound. Okay. So denoted as alpha. So their alpha is a parameter that has to be determined. And the acquisition function is UCB by some choosing a specific alpha n. There is a theory saying that what kind of alpha n you have to choose. And there is an equivalent formulation that UCB is just simply mean plus constant times the variance, the standard deviation, the mean times something. Okay, that's a basic property of the normal distribution. So if you are using GPUCB for this specific setting, you are going to choose this point. Okay, that's one criteria, very simple, right? And another criteria is called EI. Actually, this EI is the most commonly used acquisition function. It looks a little bit more complex compared to the GPUCB. To introduce EI, we need to first know what is the maximum value in the current observations. For example, if you consider start with the initial design, you have 10 points, right? So this Fn is the maximum value over that 10 points. So if you have observed 20 points, that's the maximum over that 20. And this method defines the improvement of a potential observation. Potential means that I haven't tried this point yet. Right? If you believe in your posterior Gaussian process, this potential point should have a distribution which is normal, right? Which is normal. So the improvement is defined as the so-called positive part of the difference between f of x minus your maximum one. Okay. So the positive part basically is this function. Okay. And in deep learning, there is a name called a rectifier. It's a much more fancy name. So, but in mathematics, we just call it the positive part. The function looks like this one. So if the input is less than 0, it's just 0. If the input is positive, it just takes the positive value itself. So the meaning is that if the potential observation is higher than your maximum value, then there is an improvement, because the final goal is to find the global maximum point. Okay, if the observed point is less than the maximum value, the maximum value has no change, so there is no improvement. So the improvement is 0. That's the idea behind this method. Okay. So the acquisition function is called the expected improvement criteria, usually denoted as EI. Okay. So the EI is taking the expected value of this part is the improvement given the observations. Okay. So this is a complicated function, but somehow it has an analytic formula. I'm not going to show you the formula. You can check, but if I write it down here, maybe I need to take 2 lines to write it down. But although it is complicated, but that's just for human beings. For computers, that's a really simple function to evaluate. Okay, so it can be explicitly and also as a function of the mean and the variance. As I said, eventually, actually, think about any kind of acquisition function, it always go back to the mean part and the variance part. So the mean stands for the exploitation, and the variance or the standard deviation stands for the exploration. So you are making a trade-off between two of them. And the good thing for EI is that it does not rely on a tuning parameter. There is no tuning at all, except for the parameters in the GP. Okay. So usually what we do in Bayesian optimization is that we determine the parameters of the GP at the initial stage. So once we have we finish the initial design, we can update the model parameter, and sometimes we just fix them all the way. Okay. And on the left-hand side, I show you the output of the EI method in one step. This is, of course, a single step. You can see that this point gives you the maximum expected improvement value. That means the EI criteria favors this point. As I said, GP UCB favors this point. Right? So EI gives a different choice. So you can see that of course, you can cook up similar examples in which those methods give you different answers. But in general, they have the same ideas, but just how do you trade off between the exploitation and the exploration and the exploitation? Right? If you place more importance on exploitation, you may go into this point. If you favor like exploration more than exploitation, you may consider this point. So that's a EI criteria. Of course, there are more criterions you can consider. I just list a few names: probability improvement, knowledge gradients, entropy search. Some of them are quite complicated from a computational point of view because, for example, this entropy search method, it does not have a closed form. It can be done only with Monte Carlo. You can only do Monte Carlo to compute the acquisition function. Okay. That's, as I know, EI is the most commonly used method, okay, for Bayesian optimization. Okay, so I think it's I can ramp up today's tutorial, the lecture part. The conclusion is that we have seen some advantages of using GP and also some deficiencies of GP models. The advantages are, the first one, it enables uncertainty quantification. And the GP model can also accommodate complex data structure and prior information, such as what I said in the computer experiment part. Sorry that I maybe moved too fast in that part, but what I would like to say is, because it's Bayesian, the good thing for Bayesian model is that no matter how complex the data structure is, we can use the same Bayesian rule to write down the posterior. And theoretically, or in principle, we can do the Bayesian computation if we can resolve any computational issue, then there should be no problem for the statistical inference. That's a good side of GP. Okay, and the deficiencies of GP, the first one, the computational issue actually is always the biggest challenge. Okay, so when n is large, normally we do not want to use GP anymore. That's a really big challenge. Or you can consider some improvement. Of course, some people claim they can solve for GP with really big M, but their algorithms are quite specialized. So you need to use a specialized algorithm, and maybe there's still a lot of debating why using this method if some other alternatives, some other obvious alternatives are available. But one thing I show you in this tutorial is that this computational issue can be partially evaded or rescued by choosing appropriate designs. If you are using grid designs or sparse grid designs, you can save some computational cost. Of course, the second one cannot handle discontinuous response surface. So if not only discontinuous, but also if the function space, the functions behaves quite differently in different regions, maybe the GP is also not a very good choice. For example, if in some area, the function is super smooth, and in some other domain, the function is really rough. If you have this kind of function, of course, there should be a GP that can also accommodate those functions, but you have to design your model very carefully to do that. So usually, I do not recommend you consider GP if the function, the shape of function is really weird or something. Okay, so I think I finished the 2-hour lecture for the tutorial, and the next hour, my postdoc Liang Ding will show you some hands-on part. So basically on how.
MATLAB. Is that good?
Yes.
Okay, okay. New share. Okay, let's start. So this tutorial is about how to use MATLAB to implement based Bayesian optimization algorithm. So as Ray has pointed out, a GP is a random function, so which can be characterized by a mean function and a kernel function. And in practice, you will also add a noise term to a GP. So, and you assume the data you observe in practice follow this observation, which is a GP model plus a Gaussian Y noise term. And then in this tutorial, I will teach you how to implement the GP using the GPML toolbox, and how to generate some experiment designs using sparse grid toolbox or some MATLAB built-in function. And then at last, I will also teach you how to use the MATLAB built-in Bayesian optimization toolbox to run the Bayesian optimization or the GP-based Bayesian optimization problem. So if you have MATLAB in your laptop, you can follow me and run the code on your side, because I have put all the code, all the script, MATLAB script on my slide. So the first thing we need to do is to go to the following address. So go to the Gaussian process.org, go to this address to download the GPML toolbox. And then we can directly download the zip file and unzip it and run the start script to set up the directory path, the directory path in your MATLAB. And then you can use the GPML toolbox to which give a way to define the GP random function, which is this function. So we can check its argument. So its inputs consists of the following arguments: the height, inf, min, conv, etc. So the height the high argument is a structure argument, which give you a way to define the hyperparameters for your mean function, covariance function, and the likelihood function. And the inf argument here, so it specifies how to compute the posterior, the posterior of the Gaussian process. So in this tutorial, we will use the Gaussian likelihood, but in some other situation, you can also use something like the Kullback labeler, the KL divergence, or something else as the objective functions. And then the mean here specify the mean function, the curve specify the covariance function, and the leak here specify the likelihood function. So which is the probability function of how the observations got generated. And XY here is your training set. Here XY is your training set, and XS YS is the test set. And then we can also look at the output. The output function, we have the NLC, DNLC here. So for the NLC, it represents the negative log likelihood of the GP. So say if the input is without the test set, then the GP function will return you the likelihood, the log likelihood of the observed data. And the DNLZ is a struct variable for the derivative of the NLC with respect to the parameter which you define here. And when the input comes with test set, then the GP functions will return the YMU, YS2, or these output variables. So they are just the output. They're just the output mean and the output variance. So we have a little bit difference between the YMU and FMU here. So the YMU stands for the data mean, and YS2 stands for the data variance, which is the output that give you the posterior distribution of the data. And the FMU and FS2, so the output here, gives you the posterior distribution of the Gaussian, of the latent Gaussian process. So there are a little bit difference here. And the LP variables, it's just the LP variable here. They're just the predictive, the log probability of the predictions. So so now we can run the following script to try to see how to use the GPF functions. So let me switch to the MATLAB windows. New share here. So for time saving reason, I have finished writing the code, and then what I need to do is to copy and paste and to let you see how the codes run. So this is the demo. So we first randomly generate 20 input data points here. So we can see X is 20 randomly chosen data points, and then we define 20 input noisy data associated to the input to the input X. So this gives us the noisy observations of an underlying function. And then we define 61 test points here. So now we can start defining the GP functions. So here I use a zero mean function, which is the empty functions in the GP function setting. And then I define the covariant functions as term 1/2. So the parameter here refers to the wave refers to the smooth parameter of the Martin function, Martin covariance function. And here I define the leak function as the Gaussian likelihood functions. So if I run this parameter, if I run this code, this gives us the input argument needed for the GP functions. And then I also define the hyperparameter. I saw a question here. I can't find demo.m on the package. The package download is on my slides, so you can just copy and paste. You can copy and paste the script, and then you can run it on your laptop. So
so Leon, this can only be done after the session, right? Right now, I think the audience couldn't really copy and paste. Is that right?
Oh, I can, because here. Oh, okay. You don't have access to the slide. Oh, I can share the slide here. But let's see. Stop. I can share the slide here. I can. Wait. Is or we can no. I'm not very familiar with how to do the Zoom, how to send the files on Zoom. So
okay, Leon. So for example, before you use the demo.com, can you just copy paste all the the code and then paste it in the chat box?
yes, sure.
Okay, and that way people can probably cut paste from that chat box.
Copy and
hopefully
paste.
It's not too long, right?
But I can. But I can copy and paste the. Let me try. Let me try. I don't know why, but I can copy and paste the chat box here. So let me. Like a zip file, or I can share the link on the overlap. For some reason, I can't send a file on the.
Right. So Liang, can you send the file to me through my email box? And I try to cut paste.
I can send it to Ray or
Okay.
I can send it to Ray on WeChat and then.
Yeah. I have your slides already. Let me see if I can share this file to.
I send you one. Yeah.
How to share?
Or I can.
Yeah, I have your slides. So which code are you referring to? Which?
On page 5.
On page 5?
Yes.
No, page.
So Aaron can see the.
Okay.
Or I can just explain the code here, and you can run it on MATLAB. So let's continue, and this line it indicates how to define the high struct variables, and then when you have the hyperparameter variables and you have defined the mean function, covariance function, and the likelihood function, you can put it in the minimize function. So this function, if you take the training set take the training set as the input and use the high parameter here as the initial value to and use the Gaussian likelihood function to optimize the hyperparameter to optimize the hyperparameters used for a GP process. And then you have a new hyperparameter hype2, and then you put the new hyperparameter, the likelihood functions, and all these functions defined before, and the training set and the test input into the GP functions. Then the GP function will return you a mean function and a variance associated to the mean function. So we can check the results here. So when you run the code here, it will give you the distribution, the Gaussian distribution of the data. So the gray shaded area, they are the 95% confidence interval. And the blue line here is the mean functions of GP. And the red cross here is the training set. So that's basically how to use the GP functions and how to define its arguments. So after we know how to use the GP function, we now can look at what kinds of experiment design that can give fast and accurate prediction. So this example shows that the design of the location where we have our observations play a very important role in prediction. So in one dimension, an evenly distributed distributed experiment design is better than a randomly chosen design. But in high dimensions, things become a little bit different. So now look at a naive extensions of the 1D even distributed design. So this is the 1D distribution, 1D evenly distributed design, and this is what we call full grid design. So Ray had introduced it in the last tutorial. For this design, the good news is the GPML toolbox has a particular function to compute the GP posterior condition on full grid design. And the computation is very fast. But as you can see here, obviously the number of required design points goes very fast. It goes exponentially in dimensions. So in most cases, full grid designs only works for problems with dimension less than 10. So the basic idea of fast computation of full grid is that you can decompose the computation of a GP condition on a full grid decompose it into computations of one-dimensional GP. So we now can run the following code you can run the following code to see how the full grid design can help improve the computational efficiency of GP. So here we first define two one-dimensional grid point x1 and x2, and then we use the APX grid function, which is in the GPML toolbox, we can put together x1 and x2 to make it a two-dimensional full grid. So in one dimension, so the projection of x on one dimension is exactly the x1, and its projection on the other dimension is exactly the x2. And then we define an underlying function based on this full grid design, and then we add noise to the underlying functions. So this gives us our training set, and then we use the same way to define our the input for our test set. So the APX grid functions also can give us a way that create a full grid that cover the test set and the training set simultaneously. So this function return the full grid xg that cover x and the test set xs. So the next thing we need to do is as before. What we do is to run an optimization. So given the training set, we run an optimization to get the hyperparameters for our kernel and our mean functions. And then after we have our hyperparameter, we can use this function. So this is a special function in the GPML toolbox, which is particularly for the full grid design. So if you have a full grid design and you use this function, and you put in the hyperparameter into this function, this will give you the posterior and the log likelihood of the GP condition on a full grid design. So if you run this code on full grid, then the GPML toolbox will give you a much faster way than other grid-based design. So like the Latin hypercube design or the sparse grid design. So so what we do next is to what we will do next is to look at the more general grid-based design. So the sparse grid design and the Latin hypercube design. So because they are the most commonly used design for high dimensional problem. And sparse grids imposes a higher smoothness assumption on the underlying functions. So we can use the MATLAB built-in functions to generate a Latin hypercube design. So the built-in function LHS design here, the N here stands for the number of points you're using, and D stands for the dimension or dimension of the design. And for the sparse grid design, we can go to these edges to download the sparse grid package by Plumlee. And then we can see here that this function is for generating a sparse grid design with level N and dimension D. So this is the example for using a sparse grid design and Latin hypercube design to compute the posterior of the GP. Say here I use the sparse grid design as an example, or if you copy the code here, you can also use this line. This line to generate the Latin hypercube design, but they're very similar. So after we generate the training, the input for the training set by the design function, we can also generate the output functions, the output associated to the designs here to get the observation on the underlying function. And then we use the same way to generate a 2D full grid as our test set. And the same way for defining the mean function and covariance function and the hyperparameter. And then we can put all these arguments, all these variable into the GP functions. And then if you run this line, you can get a prediction of the underlying function. And so we can see here the left graph is the prediction and the right graph is the true functions. So if you use sparse grid design and Latin hypercube design, or Latin hypercube design, because they're very efficient and they're very accurate. So even if it is a 10-dimensional problem, 10-dimensional numerical problem, you can still have very accurate prediction here. We can see they're almost the same. So the last part of this tutorial is about how to use the MATLAB Bayesian optimization toolbox to search the global minimum of the underlying functions. So very luckily, MATLAB packs all the stuff into the base up function, which take a function handle and a variable as argument and output an object that contains the result. So its input fun. The fun here stands for the target functions. So it is a function handle, and the where's here is a variable defined by the optimized variables function. So this is a function in the MATLAB Bayesian optimization toolbox. So we can also run a toy example here. If you run this 3 lines code, and then you can get the global minimum. So global minimum of the underlying functions. So I can try to run it on my site and let you see how the code works. So new sharing. So
oh gosh.
demo. So everyone can see here how the base up function works. So basically, the base up functions use the Bayesian optimizations as Ray introduced before to search the global minimum of these underlying functions. So the blue dot here stands for the observed data, and the next point, as you see before, stands for the observation.
I think we cannot see the picture.
You cannot see the picture.
Yeah, we can only see the MATLAB.
So
share the screen, not the window, maybe.
Share the screen, not the window. Share the screen. New share the desktop.
Right.
Yeah. Can you see the movie now?
Yes.
Yeah. You see here the black dot here stands for how the algorithm select the next point here. And when the algorithm stops, it give you the final result, which is the red point.
So Leon, can you rerun this example? Because I think when you switch your windows, most of people miss the beginning part.
You want me to like this? Clear.
Rerun the example. Run the example one more time.
Yeah.
Thank you.
So just 3 line. This is just a 3 line example. So you can see how the algorithm select the next point. select and then the red point stands for the result for the local minimum for the global minimum found by the algorithm. So this is the toy example, and now we can continue. You share. So can everyone see the slide now?
Yes.
Okay. And so this is just a toy example, and we can look deeper at the base of functions, because for the base of function we can choose the acquisition functions. Here for base of you have 6 choices for the acquisition functions. So the expected improvement, the EI here. So 4 of them are basically their EI, and the 5th one is the LCB, lower confidence bound, but is equivalent to the GP UCB. And the 6th is the probability of the improvement. It just they are just different way of selecting or updating the next sampling point sequentially. And the per second or per second here stands for you will use different running time for different region of the input, and plus here stands for you will add noise to the GP so that you can escape from local minimum of the underlying functions. So because I think someone has asked Ray why which one has the best performance, and I would say the performance of different acquisition function depends on the true functions, or depend on the problem itself. So as I know there are different mathematical analysis for each of the acquisition function, and most of them they are in an asymptotic sense they are equivalent, or they have similar performance. And we will also introduce the num-seed points parameters, which stand for the number of initial randomly select evaluations, because the base of functions, it just the default of the base of function, it just randomly selects 5 to 10 points as the wrong up sample, and then run the optimization, run the GP based optimization process. You can use this variable to define the number of initial randomly selected points you need, or you can use the initial X variable, which give you a way to use a particular design to define the initial points for the warm up process. So this 3 lines is the examples for running the EI algorithm with the initial designs point to, so with the initial design evenly spaced on the line. So we can look at the MATLAB windows to see how it's run. So we can see that here I define the initial design variables, which is the evenly spaced design on the interval 0 to 1, and then I also put the stopping criteria on this space of functions. So the max time here stands for the maximum of iterations of the Bayesian algorithms, which means the maximum budget for sampling is 20. And I also put so the max object evaluation stands for the budget, and the max time here stands for the maximum of time for running the algorithm. So here I set the maximum running of time as 20 seconds. So, and we can run this algorithm to see to check its performance. So this is the record of the function. We can see here that because I set the maximum running time as 20, so when the algorithm spends 20 seconds on running the optimization process, then it stops, and then it gives us the final result. But if I set a longer time, say I can set 100 here, but I set a smaller number for iteration, say just 10 here, and then I run the same code again. We can see that the algorithm stops when you have 10 iterations. So the final part of this tutorial is that we can use I use the base of function to estimate the hyperparameters of a GP. So if you have MATLAB in your laptop, you can also follow me and run the code, because there are every lines here, they are relevant to previous slides.
Liang, there's a question ask you, where do you define the acquisition function in the base op?
Oh, here you can define the acquisition function in this way. So here this is the base op function, and you can define, say, acquisition. Acquisition function, and then you set it as expected improvement. And Yeah, I think that's it. That's how you select your acquisition functions in the base of built-in functions.
So by default, which one does it use?
By default is the expected improvement per second plus. So which means you are using expected improvement, but the running time for different region of X is different, and you also add noise to the GP used by the algorithm to escape local traps.
Thank you.
Yeah, and so now we can use a final example to show how to use the base of function, how to use the Bayesian optimization toolbox to find the optimize the hyperparameters of a GP. Say here, I set the hyperparameter for my covariance functions as 1/4 and 1. So the 1/4 here is the log value of the wavelength of the covariance function, and the SF here stands for the variance of the covariance function. And here, so 1/4 and 1/10.
Leon, we couldn't really see we still see the MATLAB screen.
You still see the MATLAB screen?
Now it shows.
Yeah. So the ELL here stands for the log value of the wavelength of the covariance function, and SF here stands for the log value of the variance of the covariance function. So I set ELL as 1/4 and SF as 1. They're the true value, and then I set up the parameters for the GP as before. And now I use this parameter to generate training data X and Y, so that I can have had a noisy observations of the GP with these parameters. And then I define the target function, so which take the ELL and the SF as an input, and then it output the negative log likelihood for the observation or the training set XY associated to a GP. So this is the target functions. So our goal is to maximize this function condition on the observation X and Y. So after we have defined the target functions, we can define the optimized variables ELL and SF, and then we put them into the base of function, and we can check how the code runs in the MATLAB. Here. So base. So this is the code for generating the data. For generating the data of the underlying GP, and this is the target functions. So this is the target functions, and this code, this 5 lines code, is how to use the base op to estimate the true value true value ELL and SF here. So we can run the code now. This movie shows how the Bayesian optimizations update the sampling points. And this is the final result. And we can also check the final result and see how it's look like. So so we can see the final result is 0.39 and 0.9, and compare to the true value here, you can see that it's close enough to the true value. So that's the example of how to use the base of built-in functions to run the hyperparameter optimization of the GP.
Okay, now there are two questions. So one question a little bit earlier asked you what's the difference between best and accept. I think those are probably the different argument settings. Oh, okay, the shoot off here.
So the best is the current best value of the underlying function, and accept just mean you are the next sampling point is feasible. So which means the algorithm successfully find the next successfully find a candidate for sampling, but after sampling, it turns out the sample point is not the best one.